In this video I'm going to be talking about basic cardiac electrophysiology. There is a companion video called Basic Electrocardiograms. First, a little anatomy here. The upper part of this diagram are the atria, right and left, and then the right and left ventricles. In the upper right of the right atrium is a sinoatrial node, or SA node, which sends fibers down to another node called the atrioventricular node, or AV node, and also sends fibers over to the left atrium. So these interatrial fibers and internodal fibers carry the electrical energy across to the atria and then down into the AV node. The AV node represents a slow conducting pathway to allow the atria to finish contracting before the ventricles do. Once the electrical activity has passed through the AV node, travels down the bundle of His, and then branches off into the right and left bundle branches, and then there's also an anterior branch on the left side as well. Let's talk a little bit about the pacemaker itself. Both the SA node and the AV node act as pacemakers. So if we look at the SA nodal pacemaker, I've labeled these phases. Phase 4 is the resting phase, and one of the interesting things about phase 4 in this is an unstable resting membrane potential. There are these H channels, which are hyperpolarizing sodium channels. They're actually referred to as HCN channels, or also known as funny channels. Well, these H channels open once the membrane potential has fallen below the normal resting potential. When they open, sodium leaks in until we reach a threshold for calcium voltage-gated channels. At that point, calcium channels open and we get an action potential. Almost immediately after they open, potassium channels then open, repolarizing the cell. Once it falls below resting, the same thing happens. Sodium channels open, you get leakage current, and that reaches the threshold for the calcium channels. The SA node operates on its own without any autonomic nervous system input, and it runs at about 100 to 120 normally. I've seen studies of heart transplants in which the heart will run at about 120 beats per minute. The AV node, on the other hand, also is a pacemaker, but it runs at about 40 to 45 beats per minute. And the conduction system, primarily the bundle of His, has its own pacemaker, and it will operate at about 25 to 35 beats per minute. So if the SA node fails, the AV node becomes the pacemaker. And if both the SA node and the AV node fail, the conduction system becomes the pacemaker. Now, why is the SA node the pacemaker? Simply because it has the highest rate of diastolic depolarization. That means that it's going to trigger all other pacemakers before they can trigger themselves. So the SA node will send a signal down to the AV node while the AV node is still trying to reach threshold and stimulate it immediately to reach threshold. And then the conduction system will also be stimulated. So the pacemaker with the fastest rate of diastolic depolarization becomes the dominant pacemaker. Parasympathetic stimulation hyperpolarizes the membrane and decreases H-channel open probability. This reduces the leakage current, slowing the rate of depolarization to threshold, decreasing the pacemaker frequency. Also, hyperpolarization rapidly inhibits the pacemaker. The sympathetic nervous system stimulates the SA node by increasing H-channel open probability, thereby increasing the rate of depolarization and increasing the heart rate. And in this little diagram we can see the middle one here in green is the control. We see a gradual increase in depolarization, thresholds reach, we have an action potential. Sympathetic stimulation causes a more rapid increase to threshold, causing the beat to come more quickly. And the parasympathetic stimulation does two things: hyperpolarizes the membrane and slows down the rate of depolarization so the next beat comes later. So how does that work intracellularly? Norepinephrine stimulates a G protein, in this case GS, which activates adenylate cyclase, causing ATP to become cyclic AMP. Cyclic AMP activates protein kinase A. Protein kinase A then phosphorylates sodium channels, opening up these sodium channels, or holding them open for a longer period. It also affects calcium channels, but I'm not going to talk about these calcium channels or the sarcoplasmic reticulum, just talking about rate. Parasympathetic nervous system does two things. First thing it does is to open up potassium channels. So a rapid hyperpolarization. It also triggers nitric oxide synthase to create nitric oxide. Nitric oxide stimulates guanylate cyclase to create cyclic GMP. Cyclic GMP then stimulates phosphodiesterase to break down cyclic AMP into 5' AMP. But it also inhibits adenylate cyclase by a GI inhibitory G protein to inhibit adenylate cyclase. So we're not making cyclic AMP, and we're rapidly reducing any cyclic AMP present. That keeps these H channels closed for a longer period of time, or more H channels close. In other words, the leakage of sodium in slows down. The autonomic nervous system stimulates both of these nodes. Parasympathetic and sympathetic both stimulate the SA node and both stimulate the AV node. The sympathetic nervous system, however, has another branch which innervates the cardiac myocytes, the ventricular cardiac myocytes, to cause an increase in contractility, force of contraction. Interestingly, the right vagus nerve and cardiac sympathetic nerve predominantly affect the SA node, not exclusively, and the left parasympathetic and sympathetic nerves predominantly innervate the AV node. This was taken from some of my work back in 1985, in which I isolated the vagus nerve and the cardiac sympathetic nerve, and then this bar represents stimulation. You can see a rapid decrease in heart rate. These are very high heart rates, by the way. A rapid decrease in heart rate, and then when the stimulus is taken off, the heart rate increases also rapidly. The sympathetic nervous system, on the other hand, if we stimulate it, takes about 30 seconds to reach maximum heart rate. And when the stimulus is removed, conversely, we get a slow reduction in heart rate. The rapid change in heart rate by parasympathetic activation and deactivation is likely the result of the more rapid hyperpolarization and then depolarization or repolarization back to normal, where the sympathetic nervous system just does not do that. Just to remind you about normal nervous and skeletal muscle action potentials, sodium conductance rises, it reaches threshold. We see a rapid increase in sodium conductance. Sodium channels rapidly inactivate. Conductance then rapidly decreases. But during this increase in sodium conduction, we get a rapid increase in voltage. In other words, action potential. Potassium channels now open right as the sodium channels inactivate to increase the rate of repolarization of the action potential. This period between depolarization and returning approximately to the threshold again, we call the absolute refractory period. And it's absolute, which means you absolutely cannot get another action potential. However, extra potassium channels that open cause the membrane potential to fall below resting, leading to a relative refractory period. Relative because you can get another action potential, but you have to get the voltage higher to trigger it. As these potassium channels close, membrane potential returns to normal. But that differs from a cardiac action potential. We still get rapid sodium conductance, then inactivation and a loss of sodium conductance. But as sodium is entering the cell, potassium is leaving. The positive charge coming in is forcing potassium out. But very quickly these potassium channels close. And by closing these potassium channels, we inhibit repolarization. And at the same time, we're opening up calcium channels. Opening calcium channels leads to an increase in the positive charge entering the cell, holding the membrane potential high. Potassium channels then open, calcium channels then close, and we repolarize the membrane. Now I'm going to dim this and place the ventricular action potential on top in red. We can see in phase 4 is our resting phase. Phase 0 is the rapid uptake of sodium and increase in the voltage. Potassium then is forced outward, and we see a partial repolarization. We call that phase 1. But incomplete repolarization occurs because potassium channels close, calcium channels open. We see a plateau phase here, which is phase 2. During potassium exit and the loss of calcium entry, we have our repolarization phase. Call that phase 3. And we'll go from somewhere around minus 85 millivolts up to maybe 25, 30 millivolts. Well, that concludes the talk on the ventricular action potential. You might next want to move on to the basic electrocardiogram.